Hello, we're continuing with applications of integration, and today we're looking at work. Okay, so this is a topic in sort of applied mathematics, perhaps physics, where we're going to calculate how much work is being done, perhaps lifting an object or moving an object or something like that. There's no real overarching theorem to today's work. However, there is kind of a technique we'll see where we break the amount of work we have to do up into little pieces, and of course, as we've seen lots of times, that will eventually result in an integral. Okay, so first we need our definition. Okay, so work is the action of a force which moves an object. Okay, that seems fairly straightforward and pretty intuitive. And we write it like this: W equals F times by D, where F is force and D is distance. So the amount of work done is force multiplied by distance. And again, that sort of intuitively makes sense. Okay, the more force we have to do over a large distance, the more work that is done. Just in terms of the units we use for this, so force is measured in newtons, distance is measured in meters, and work is measured in joules. We can also measure work in Newton meters. You'll see it occasionally written like that, obviously because it is force times by distance. So joules will be our SI units. We also have imperial units, and I think we will see an example where we use those. Force here is in pounds, distance is in feet, and work, therefore, is in foot-pounds. Those two multiplied together. Okay, so we'll start with a very simple example. So suppose we have a 400-pound object, and we're going to lift that up 6 feet. Okay, nothing too complicated there. It's a fixed weight and distance. So it's simply 400 times by 6. So we get 2,400 foot-pounds of work. And that's about it. For a simple object where the force is unchanging, we simply multiply and that's about it. But of course, what we're going to be more interested in is what if the force varies? Okay, what if over time the force needed varies? Okay, well in that case, the total work done is going to be the sum of lots of sort of little pieces of work done, the WIs here. And we'll calculate each of those WIs to be the force at some point in time multiplied by some small distance, this delta xi. Okay, and again, this should look familiar to you. Now we take the limit as n goes to infinity of all these little pieces, and we result in an integral. So this is our key idea. This is our idea for today. So f of x is some sort of continuous function, and that is the amount of force we're applying to move some object. And we're going to assume we're moving it from A to B. Then the total amount of work done from A to B is simply the integral from A to B of that f of x dx. Okay, so that's the integral that results, that gives us our work. Okay, so let's take an example. So let's have a 50-meter rope. We'll assume that it's 0.2 kilograms per meter. That's the density of the rope. And we'll assume it's hanging over the edge of a building. In fact, let's take a diagram here. There it is. It's got this little pulley. And we want to know how much work is done pulling the entire rope to the top of the building. Okay, so we're going to pull it up over that pulley until it's all at the top, and we'll have a part B to that too. How much work is done pulling it the first 20 meters? Okay, so the first thing to say is, well, why is the work varying here? Well, think about this. As we lift this rope up, the amount of rope that's kind of left to lift up is decreasing. Okay, as the rope goes higher, there's less rope left to lift up. Therefore, the amount of work we're actually doing is decreasing there. So let's think about the force we need to apply at some sort of height x. Okay, so assuming the rope is at some sort of height x, well, the force we have to apply, oh, and yes, this is important. We have this 9.8 here. So that's, you'll often see this referred to as G. Okay, that's gravity, basically. That's the gravity that we have to apply. We have the 0.2, which is how many kilograms per meter we have. And then the 50 minus x, well, if the rope is at height x, I guess the bottom of the rope is at height x, the amount of rope we have to actually pull up is 50 minus x. So that's how much rope we have there. And therefore, at any particular point in time, f of x is given by this. Therefore, at the height x, the amount of work we have to do to pull up the rope, just a small amount, delta x, will be given by this. We multiply the force by the distance, and that will give us the work. And of course, what we saw from the key idea, that's going to result in this formula. Okay, the 1.96 is just 9.8 times by 0.2, and then we get 50 minus x, and of course we integrate that from 0 to 50, Okay, and of course, we see this a lot when we're doing these application integration. The actual integral is very simple. Okay, and so we just plug in and we get 2,450, and remember the units here were joules. We're working with the SI units of joules. Okay, so that's part A. Part B is actually very straightforward. Given what we've already seen, we simply integrate that from 0 to 20 instead of 0 to 50. And so the amount of work we do there is 1568. And you'll notice, if we just go back 1 second, the 2450 compared to the 1568, we do more than half of the work in the first 20 meters, and that's because it's more work at the beginning, as simply more rope to pull up there. Okay, so let's move on to another example, and here we're going to use Hooke's law. Okay, so Hooke's law says that the amount of force we need to either compress or stretch, so to push in or to stretch out a spring, x units from its natural length, is proportional to how far it is from its natural length. So the f of x is equal to kx for some constant k. And again, this is kind of intuitive, I think. Okay, if you think about a spring, if you just leave it in its natural position, no force at all. As you try and, let's say, stretch it outwards, the further you go away from that natural position, the harder work that becomes. And the same applies as with compressing it. The further you compress it away from its natural place, the harder that is. Okay, so that's Hooke's law. That applies to springs, and so let's apply this. So a force of 7 newtons stretches a spring from its natural length of 11 centimeters to 21 centimeters. Okay, so that's how much force we need to go in that 10 centimeters. How much work is done in stretching the spring from 16 to 21 centimeters? Okay, so the first thing to note, this is always very important with these Hooke's law type questions, its natural length is 11 centimeters. And that's kind of our base. If you like, that's our zero. Okay, it doesn't really matter what it is, we just treat that as our zero, whether we're compressing or stretching. How far away from that point are we? Okay, and the very first thing we have to do, we're going to use that top part to find k. Okay, so kx is equal to 7, that force of 7 newtons. Therefore 0.1k is 7. And I should note the 0.1 here. So we're going from 11 to 21, so we're going a total of 10 centimeters. But again, if you recall our SI units, we have to treat these in meters rather than centimeters. So if we're going 10 centimeters, it means we're going 0.1 meters. Okay, so we get 0.1k equals 7. So of course k equals 70, and that's 70 newtons per meter. I'm going to put units on that. And okay, so now we can actually answer the question. Okay, how much work is done in stretching the spring from a length of 16 to 21? Well, so the 16 is 5 centimeters more than the 11. The 21 is 10 centimeters more than the 11. Therefore, and we're integrating this sort of 70x. Therefore, our integral goes from 0.05, and again, just transferring 5 centimeters into meters, 0.05, and the 10 centimeters into meters is 0.1. So we're integrating from 0.05 to 0.1 of 70x dx, and again, it's a very straightforward integral, and we end up with 0.2625 joules. Okay, so as I say, there'll be various other examples that you'll see in the book and in the homework questions, and hopefully you'll see in class. This is just a couple to give you an idea of how these questions are done.